Hello and welcome to this Deakin University alumni webinar presented by Dr. Ellen Moon. Sam Johnston here from the Deakin Alumni Relations team. It's great to have you with us. I'd like to start by acknowledging the traditional owners of the land from which we're broadcasting today, the Wadwurrung people of the Kulin Nations, and to pay our respects to their elders, past, present and emerging. Today we're broadcasting from Deakin's Waterfront campus, and our webinar topic is Environmental Engineering in the 21st Century, Why We Should Sweat the Small Stuff. To watch past webinar and seminar recordings, you can visit the webinar and resources page on the Deakin alumni website. Our presenter today, Dr. Ellen Moon, is a lecturer in environmental engineering at Deakin University. Her research focuses on contaminant transport through landscapes and metal removal from water-based systems. Her work combines fieldwork, lab work, and synchrotron-based analyses to understand the molecular scale relationships between metals and surfaces. Ellen received her PhD from the University of Southampton in 2012. She moved to Australia in 2011 and since then has worked in both industry and academia on a range of projects, including improving the sustainability of industrial processes and assessing the resilience of remediated landscapes in a changing climate. She is passionate about engaging young people in STEM and in recognition of her outreach and research was named as one of Science and Technology Australia's 60 Superstars of STEM for 2019 and 2020. Thank you for joining us today, Ellen. Over to you.
Thanks very much. I'm excited to talk today about some of my research that I've been undertaking recently and also some of my perspectives on gender equity in STEM as well. So there we go. So one of the questions that I get asked a lot is, what is environmental engineering? I think it's not necessarily as obvious to everybody as what civil engineering or mechanical engineering entails. So environmental engineers work across a range of sectors. We work with industry, with commercial clients, with government, with local governments as well. And the main focus of our work is understanding the health of the air, the land and the water, assessing the impacts of projects past, present and future, and developing solutions to minimise effects of those projects. Sometimes that might be to mitigate future effects, or it might be designing remediation strategies to clean up the effects of past projects. Environmental engineering is a really broad discipline and it covers off on lots of different aspects. And if you choose to study environmental engineering at Deakin, you will certainly be able to cover off on all of these during your course. So environmental engineers are concerned with air and noise pollution, with sustainable infrastructure, with energy generation, with catchment management, remediation of land and water, with water treatment and with waste management and recycling. And a lot of these all feed in under the kind of broader topic of public health, how these factors influence the health of the environment and therefore the health of the people that live and interact with that environment. But my particular area of interest, as Sam just described, is heavy metals in landscapes. I'm really interested in understanding how heavy metals move through landscapes, understanding the kind of risks that they might pose, and if they do pose a risk, designing remediation strategies to clean them up. And my work is a combination of field work, so going out collecting soil samples, water samples, bringing them back to the lab, to the great facilities that we have at Deakin, and analysing the samples for various properties there. And I often take my samples to some of the advanced facilities that we have here in Australia, including the Australian synchrotron in Melbourne and also the Australian Centre for Neutron Scattering in Sydney. And these allow me to really interrogate my samples down to the molecular scale to really understand what's going on, how the heavy metals are interacting with the soils and the waters that I've been sampling. So this picture here, which is a mine site, you can tell by the bright colours there in the water that there are heavy metals present. This is kind of my bread and butter. This is the sorts of challenges that I really enjoy working on. And to sort of explain how I approach my research, I think it can be useful to switch to a slightly different kind of picture or a slightly different kind of landscape. And so the metaphor that I like to use for the way I approach my work is this picture, the painting, beautiful painting by Monet, the Water Lily Pond. If we look at this in terms of the big picture, so taking it in, we get a pretty good understanding of the scene that Monet saw that day and that he wanted to recreate. We've got a bridge over a water lily pond. We can tell it's a pretty calm day. We've got some reflections in the water there from the weeping willows. But if we take a slightly different approach and we zoom in and we interrogate the detail, that's when we get a much richer understanding of that scene and the complexity and the intricacies that Monet saw that day. So we suddenly appreciate how bright the colours were, how vivid, and what a range of colours he saw. We see the way that he used the paint and the texture of the canvas to really bring to life that scene and give it a kind of 3D nature. And so instead of just taking in the big picture, if we are able to take the time to zoom in and delve into that detail, we can really improve our understanding and get a much richer picture of what's going on. And this same kind of rationale applies to my work. So here, I'm really interested to delve into this sort of interface between the soils and the sediments and the water in these natural or sometimes unnatural landscapes like this tailings pond here. And when we delve in, what I'm looking to understand is the way that the heavy metals interact with the water and also with the sediments and soils that are present. So this image that you can see now, what it represents, what these grey shapes, these octahedra towards the bottom of the picture, they represent the minerals that make up the soils and the sediments. And then above that, we've got our water molecules, which are the little greyed out ones that look a little bit like Mickey Mouse heads. So we've got our oxygen with 2 hydrogens. And then the bright coloured atoms that you see there are heavy metals. And so when I take my samples to the synchrotron or to the neutron scattering facility, what I'm looking to understand is the behaviour of those metals. So I'm looking to identify which metals might be dissolved. So these are going to be very mobile. Because they're dissolved in water, they move very easily through landscapes, and they have the potential to pose risk and to cause problems that way. I'm also looking for metals that might be loosely bound onto sediments. So these are metals that are still often surrounded by a layer of water molecules, and they're attracted or they're held onto the surface by an electrostatic attraction. So this is fairly easily reversed, and it only takes very subtle changes in water chemistry for these metals to become mobile again and to be easily transported through the landscape. I'm also looking for tightly bound metals. So these are metals that have actually formed chemical bonds with the mineral surface. So they're very tightly held on, and they require more pronounced changes in water or soil chemistry to release these metals. So usually these don't cause a problem, but we still have to be mindful that changes can lead to increased mobility of these types of metals. And the final type I'm looking for is metals that might actually have become structurally incorporated into the minerals. So they're actually locked away inside the mineral structure. And this is kind of our ideal scenario for heavy metals, because it means it's very challenging. It requires very big chemistry changes for these metals to be released from the mineral structure and potentially cause harm. So you might ask, why does it matter? Why do we really care how the metals are bound onto a mineral surface or if they're dissolved? So if we were to take a big picture approach to that, say we were just to measure the distribution of metals between the dissolved and the solid fractions, that might tell us which of the metals are most mobile, but it would only tell us that under the very specific conditions at which we tested that water. It would also, by giving us a clue of which metals were mobile and which weren't, it would give us some clues towards the ways that we might approach remediation, but we would ultimately still be having to take a trial and error approach because we don't really understand the chemistry very well. But if we take this molecular level approach, trying to understand exactly what nature of bonding these metals have with the mineral surfaces, then we can find out so much more about the system. So if we're able to determine the chemistry of the dissolved metals, this really helps us to understand whether they are bioavailable, or perhaps even though they're dissolved, they're not able to be taken up by plants or animals. And it also gives us an indication of the toxicity of the metals, because that chemistry of which they're dissolved in the water actually really matters for whether they're toxic or not. By determining the types of bonding between the metals and the solid phase, that can help us to predict the resilience of the system to outside influences. So we're able to gauge what types of chemistry changes might result in the metal releasing or not. You know, is it as simple as if the water was to become more salty, would that release the metal? Or perhaps it's a tighter bond, and so what we actually need is a big pH change of the water for that to happen. And because we know so much more about the chemistry of the system, we're then able to design much more targeted remediation strategies that are much more likely to work and much more likely to stay remediated under future challenges or future climate situations where the chemistry might be a little bit different again. So how do we put this into practice? To demonstrate the importance of this molecular scale understanding, I wanted to talk about a project that I did a couple of years ago, which focused on uranium mineral processing in Australia and whether or not we can use salty water in processing circuits. So the motivation behind this project was that we know that the demand for nuclear energy around the world is expected to triple by 2050. And Australia currently holds 40% of the world's uranium resources, so it's likely that we will play a very important role in that expansion in nuclear energy, whether nuclear energy itself comes to Australia or not. Uranium processing, however, requires really large amounts of groundwater. This is a challenge because an awful lot of our uranium mines are currently in really arid locations in Australia, and access to groundwater is difficult. And as we know, groundwater is a very precious resource. So, for example, Olympic Dam, which is one of our largest mines, uses 10 Olympic-sized swimming pools worth of water per day. So if we were able to substitute that groundwater, that fresh water that we could be using for other purposes, with seawater or even salty wastewaters, that would be much better for the environment. It would be much better for our agriculture sector, and it would ultimately be a lot more sustainable. However, we know that salt, and in particular the chloride part of sodium chloride, negatively impacts the uranium extraction circuits, but the chemistry of this system is not well understood. So we set ourselves the challenge of trying to better understand this chemistry. If we could identify the molecular level mechanism at play, so exactly how the chloride negatively impacts the uranium extraction, then perhaps we could adapt our uranium processing circuits to overcome that. So that's what we set about doing. So I mentioned that we knew that salt negatively impacts uranium extraction. So what this graph shows is on the vertical axis, we've got uranium extraction. So 100% is what we're hoping for. We want our extraction process to be as efficient as possible, so 100% is the target. And along the horizontal axis we've got the salt concentration of our uranium processing liquor, and so it's increasing. What the levels there represent are very salty waters. Seawater is sort of around about 1 to or less than about 0.5 to 1 molar, depending on where you are. So that's on the lower end of the spectrum, but we do often get wastewaters and some groundwaters that are much, much saltier than that. So we can see that as we increase the salt concentration of the uranium feed liquor, the extraction drops off quite rapidly, all the way down to around about 30%. And this was always supposed to be due to chloride competition. It was negatively impacting the extraction. But what we see as we push that salt concentration up even higher is that the uranium extraction picks back up again. Now, this tells us that chloride competition probably isn't the reason for this. Then there must be something else happening. So we wondered if the uranium chemistry was changing as we increased the salt, and maybe this had something to do with it. So uranium extraction happens through a process called ion exchange. It's very much like the loosely bound metal scenario that I described to you earlier, except rather than having minerals, your soil and sediment, we have these little orange beads that are known as ion exchange resins. They have chemical groups on their surface that are able to attract metals from solution, in this case uranium. And what happens is that one of the groups that they have essentially swaps or exchanges with the uranium, and the uranium remains loosely bound on the resin surface, and then we use a different type of chemistry then to take the uranium off once it's sort of so that we've got then a purified uranium solution. And what we thought was happening was that when we had salty water, rather than the uranium being taken up by the resin, it was actually taking up the chloride instead, and that was responsible for the drop-off. But as you saw from the previous graph, the fact that the uranium extraction increases again tells us that this probably isn't at play. So we wanted to find out what was. So we took our samples along to the Australian synchrotron. This is a fantastic facility in Clayton, in Melbourne. It's a particle accelerator. It accelerates electrons to almost the speed of light, 99.999% the speed of light. They whiz around and around and around the storage ring, and as they move, they give off light, which is known as synchrotron light. And this is really, really useful to scientists and engineers because it allows us to interrogate our samples. It's very special light. It's incredibly intense. In fact, it's 1,000,000 times brighter than the light that comes from the sun. And this means that we're able to test our samples very quickly and get very high quality data back from our samples. The light that it gives off is available across a very broad range of energies or wavelengths, all the way from infrared up to X-rays. and the light that it gives off is tunable as well. So we're able to select a very specific wavelength that we want to use to get the most information we can out of our samples. So we took our ion exchange resin samples along that had uranium on and that had been taken up from different parts or different concentrations of or different liquors made with different concentrations of salt. And we used a technique called X-ray absorption spectroscopy. We tuned the energy of the synchrotron light to target uranium very specifically. And using this light at the right wavelength, we were able to generate data that could tell us the position in space and the chemical identity of the neighboring atoms that surround our uranium. And what we found across our samples was 3 distinct types of uranium chemistry. So at very low salt concentrations, we had the uranium chemistry that you can see here on the left-hand side of the screen. At the very high salt concentrations, we had the uranium chemistry here that you can see on the right of the screen. You can see that this molecule looks quite different. And then in those sort of intermediate salt regimes, we had a kind of intermediate chemistry of uranium, something that looks a little bit like the one on the left and also a little bit like the one on the right. And this was a really important result for us because when we took these 3 different types of uranium chemistries and put them against the concentrations of salt that that the liquors had come from, we saw that they matched up almost perfectly with the 3 different regimes of our uranium extraction graph. So where we see very high uranium extraction, so up close to 100%, we had this type of uranium chemistry, which has a very high affinity for the ion exchange resin. So we're able to extract almost 100% of the uranium that's available in the feed liquor. In this sort of intermediate regime, what we find is a uranium molecule that doesn't have a very great affinity for the ion exchange resin. And what we think was happening here is that the chloride from the salt solution actually has a much stronger affinity, and so it was being taken up then. And that's why we see this big drop-off in the uranium uptake. But when we move into this high salt concentration, the type of uranium chemistry that we have, once again, has a much stronger affinity for the ion exchange resin and is able to outcompete the chloride and actually be taken up by the resin. And so we see this increase in uranium extraction again. So bringing this all back to the big picture versus molecular level sort of approach. By thinking about this in terms of the big picture, we were able to get as far as saying chloride has a negative impact on uranium extraction. Although we could see that once we increase the salt concentrations much higher, then we're able to extract more uranium again. And this indicated to us that there was a possible uranium chemistry change, but we weren't able to really pin down what it was or say that for sure. But by delving in at the molecular level, so using the Australian synchrotron to interrogate our samples down to this molecular level, we could see that increasing the chloride concentration in the processing liquor resulted in 3 distinct uranium species over the 3 concentration ranges of salt. And this, in turn, explained the uranium uptake curve and that strange shape that it had. So the overall outcome of this is that now we know how chloride affects uranium chemistry. We're able to tailor the liquor chemistry or indeed the resin chemistry to be able to increase the uranium extraction to 100% regardless of which of those uranium chemistries we have. And this hopefully in future will enable the use of salty water in mineral processing circuits, saving an awful lot of fresh water from being used. So this type of big picture versus molecular level approach I've used a lot during my research, and I just wanted to give another quick example of that before we move on. And this was another project with industry partners. So the challenge here was that there had been a build-up of sediment in the boating channel of an estuary over in WA. The local council wanted to dredge the sediment out of the boating channel because it was inhibiting recreational fishing and also commercial fishing. But they were worried that by dredging the sediment, they might be introducing water quality issues. So we did some bulk analysis of the sediment that was building up in the boating channel, and it told us that it was pyrite, which is traditionally seen as a very stable type of iron mineral. It often has metals locked away inside or tightly bound to the surface, but pyrite generally needs quite big changes in chemistry to allow it to release those metals. So it was presumed that there would be very little water quality consequences of dredging these sediments. However, we did also delve in at the molecular level, and what we found was that indeed the sediment is composed of pyrite, but it's actually extremely fine-grained pyrite. So we're talking grains on the nanometer scale. They're very, very tiny. And what this means is that it's not like normal pyrite, which occurs in much, much bigger particles. And because it's so fine-grained, it can be rapidly altered by fairly minor changes in chemistry. And what we were able to show was that the disturbance caused by the dredging, which ultimately reoxygenates the deep water, was resulting in the pyrite being altered and releasing these metals into the water. This was causing water quality impacts on the short term, but the interesting thing was that on the long term it wasn't, because the mineral phases that the pyrite was transforming into were then able to recapture a lot of these metals that had been released into the water. So although there were moderate short-term water quality impacts, in the long term, actually, the water quality impacts were fairly minor. And so this gave our industry partner enough sort of confidence to be able to say that, that the dredging was a suitable strategy for them to move ahead. But it was only by delving in at this molecular level that we were able to understand the subtleties in the differences in the water quality impacts over those temporal changes. So this type of molecular level approach is useful across a lot of different types of environmental engineering. I myself have used it for remediation of land and water, and I've also used it in terms of water treatment and in terms of waste management and recycling for extracting heavy metals from waste materials and that type of thing. And all of these come together and sort of show that this type of molecular level approach can be very useful for public health as well. And indirectly, it's also very useful for pretty much all aspects of environmental engineering. And in the future, I can definitely see that it's going to be increasingly important for developing sustainable infrastructure, and importantly in energy generation, because a lot of our renewables technology, specifically those requiring batteries, have very high demands of heavy metals. And so the mining sector and also the waste management and recycling sector are going to see a lot more need for being able to separate heavy metals and deal with them appropriately. So I've already talked about how engineering, environmental engineering is the type of career that can lead to many opportunities. And because I do like a bit of a visual metaphor, I like to think of that as the kind of branching of a tree. So there are many different avenues that an education in environmental engineering can take you down, whatever sort of interests you. But similarly, a bit like the roots of a tree, there are many different ways by which you can get into environmental engineering or engineering in general, I think. And this is one of the great strengths of studying STEM at university or pursuing a career in the STEM sector, in that the skills that you develop, that you learn, are going to be very useful across multiple sectors. And so it can be quite easy to find your way into the area of STEM that you really enjoy from multiple different original pathways. And I think my career has been a good example of that. So I actually studied chemical physics at university. I didn't do engineering. I studied in Bristol, and I took as many opportunities as I could while I was a student. And one of those that really shaped my future was a conservation biology internship that I took on in Madagascar, where we were studying the health of the coral reefs. And this really piqued my interest in this sort of interplay between the chemistry of the earth and the chemistry of the water, because Madagascar at the time had been experiencing a lot of deforestation, and there was a lot of sediment runoff to the coral reefs, and we were really able to see how that was impacting the biodiversity, and it made me want to know more about that kind of thing. My career took a little segue, I suppose. After my degree, I went back to Jersey in the Channel Islands, where I'm from originally, to test the waters of finance, to see if I would enjoy a career in finance. I'd had a very mathsy-based undergraduate degree, so I thought maybe finance would be a good option, but it didn't really suit me, didn't pique my interest in the way that that science had, and so shortly afterwards, I started my PhD in geochemistry, really inspired by that time in Madagascar. So I was here able to study how heavy metals interact with sediments and what this means for the kind of deep ocean sediments, how they're affected by volcanic eruptions, and also how our soils on land are affected by the kinds of metals that we use a lot in pesticides and fungicides, for example. This was also where I was first introduced to synchrotron science. It's something that's been a part of my career since then. So from that very sort of fundamental chemical physics training, I was able to shift into a more sort of applied earth science area. And then I shifted further into the sort of more applied sector and was able to transfer those skills I developed to the mineral processing industry, including the uranium processing project that I talked to you about earlier. And this was a really interesting time for me. I was able to understand a lot more about how industry research works, the types of challenges that are important to industry, and I was also able to share my expertise in synchrotron science and show these types of industries how important this kind of molecular level or fundamental understanding of their systems can be. I really enjoyed my time in industry, but I missed being on the other side of the fence, sort of cleaning up challenges and feeling like I was doing good things for the environment. So I took up a research position with a focus on remediation of contaminated land. This was a really exciting project focused in North Queensland on an acid sulfate soil contaminated site. And this was really excellent because I was working with a lot of geochemists who shared my passion for this sort of molecular level understanding, and we were really able to develop an excellent remediation strategy based on knowing the intricacies of how the system was working. This led me to my lectureship in environmental engineering. I really enjoyed being able to apply the things that I'd learned to helping the environment. And that's what I've been able to do here at Deakin. And perhaps the most exciting opportunity of my engineering journey so far came to me last year when I was able to travel to Antarctica on a 3-week voyage. So that's my engineering journey. And as I said, I think it is a good example that a training in STEM can really help you move around and follow your interests, because a lot of the core learnings that the STEM disciplines share are very applicable across others. One of the things I did notice through my career in STEM has been the gender balance, or the lack thereof. And I think it's probably quite plain to most people working in the STEM sector that women are underrepresented. And there are many, you'll hear a lot of rhetoric around why that might be. Everybody's sort of got an idea about what's causing it. But I think what's really sort of helped me, or what's really made me passionate in this space, in sort of wanting to get more women into STEM disciplines, is again taking this approach where we delve that little bit deeper. It's easy to see the big picture, but what's happening when we look and we zoom in at the detail? And what has become quite clear is a phenomenon that's known as the leaky pipeline. What this loosely means is that women come into STEM careers reasonably well represented, but as they get to more and more senior positions, the representation gets less and less. And and that's, I think, what we need to interrogate as to why that is. And when I think back to my own experience, actually, that is really reflected amongst the women that I know from STEM. So this is my graduating cohort from the University of Southampton. This was 2012, so 7-8 years ago now. And in that time, a number of the women that I graduated with are no longer working in the STEM sector. This is pretty much par for the course, it seems. So this is the STEM leaky pipeline, and here STEM is with a double M, so science, technology, engineering, maths and medicine. So what we see is that the number of staff identifying as female at the kind of graduate or entry level is actually 50% in Australia. But as we get through to more senior levels, middle management, then senior management, the representation of women drops off to the point that at executive level, it's as low as 16%. In engineering, the pipeline's shape is almost identical, except the starting figure is much lower. Graduates and entry-level women account for 25% of engineers, and by the time we get to executive level, it's down to 5%. So why does this happen? There's been a lot of research into this. It's quite clear that there is a caregiver's penalty. This, of course, doesn't just affect women. It does affect men who are caregivers as well. But overwhelmingly, women are much more likely to be primary carers to children and also adults. And women are much more likely to work part-time or not at all to accommodate caring responsibilities than men are. And this impacts the STEM sector in particular, because many STEM workplaces are incredibly inflexible in terms of the hours that they allow their staff to work, where they allow their staff to work, and things like that. And there's also a very traditional view of competency in a lot of STEM sectors. It seems to be measured in terms of outputs, whether that's journal articles written or reports produced or clients won or dollar value on clients' projects. And a lot of those things are actually directly correlated to the amount of time you can invest. And when you have a very busy life outside of work because you have a lot of caring responsibilities, it can be hard to invest that same amount of time. Therefore, your outputs are less and your competency is viewed as less. Another real challenge to women in STEM is the phenomenon known as unconscious bias. Now, this is something that everybody has. It's the way our brain functions, and it's the product of our experiences in our lifetime. It's shaped by the media, by our friends, our family, their opinions, and by the way that we were brought up. But there are two particular types of unconscious bias that really impact women in STEM. One is a competency bias. There's research to show that women must actually be twice as productive as men to be viewed as equally competent. So this is a real challenge, particularly when it's compounded by caregiving responsibilities. There's also the similarity bias, and this is the bias by which we're all more likely to support or choose or advance those who remind us of ourselves. So in situations or in sectors that are already male-dominated, similarity bias can result in the propagation of this type of environment, just because people are more naturally drawn to people who remind them of themselves. So why is it a problem that we have a leaky pipeline in STEM? You know, we see engineering firms seem to be ticking along okay, don't they? But the question is, could they be ticking along better? So research shows that diverse teams make better decisions. And this isn't just because they generate a broader range of ideas, but because diverse teams actually weigh up the available information and options far more thoroughly and fairly than non-diverse teams do. And this is going to be important because, let's face it, we've got some fairly monumental challenges ahead of us as engineers. Climate change is presenting all sorts of challenges for us at the moment, as we know in Australia, as we see part of New South Wales and Queensland ravaged by bushfires presently. We have extreme water security challenges here in Australia, and we have energy generation challenges in Australia too. And engineers are going to be part of creating the solutions to those. Let's face it, the ways we've been approaching this at the moment don't seem to be working. So new, fresh solutions are required. And this could perhaps be found by increasing the diversity of our teams that are trying to tackle them. But if you're a little bit more mercenary in terms of your approach, then there's also a real financial incentive to increasing the diversity of your teams. Companies with the best gender diversity consistently outperform their competitors by significant margins. And it's interesting to note that cultural diversity is a really strong indicator of financial success as well. So this is a very timely reminder that diversity is not just about gender, it's about all aspects, including all parts of society in our teams. So what can we do to tackle some of these challenges? I think we can work on 3 different levels. So at that individual level, we can be aware of our own unconscious biases. We can't get rid of them, it's just the way our brain works, but we can be aware of when we're making a decision, and we can question ourselves, am I making this decision based on fact, or are my biases creeping in? We can also champion people from underrepresented minorities. We can put them forward, encourage them for promotion. We can give them opportunities. We can also stand up for them if we hear casual racism or casual sexism in our workplaces, and tell people that it's not acceptable. At that workplace level, we can fight for more flexibility in our workplace. These days, there's very little reason why more flexibility couldn't be built in, whether that's in terms of job sharing, whether it's flexible working hours, whether it's flexible working locations. And really importantly, we need the buy-in. We need to include the senior men in these changes that we want to implement. We've seen from the leaky pipeline that overwhelmingly those in the senior positions are men, and so we need them on board. We need them to be part of this change so that we can diversify all of our workforces for the better ideas generation. On the national level, I think we can change the way we talk about STEM careers, not only in terms of careers that might be suitable for boys or girls, but also in the way that we talk about careers like engineering that have traditionally been seen as somebody wearing a hard hat, building a bridge or building a car. You know, engineering, you can really make a difference by being an engineer. And these days, there's so much more involved, from, you know, the novel materials that are being developed to protecting the environment as an environmental engineer, to being an electrical engineer who's changing the way that power systems are evolving. So there's a much broader way that you can make an impact as an engineer than perhaps there were in the past. And finally, we can get behind some of our national strategies. For example, the Superstars of STEM program set up by Science and Technology Australia, which I have been lucky enough to be a part of. The Superstars of STEM aims to challenge society's gender assumptions about scientists. They've hand-selected 60 of the top female scientists across all disciplines in Australia, and are working really hard to help us to get our stories about our research, our careers, and our passion out there, so that young women and girls and boys around the country have increased access to female role models in STEM. And importantly, they've been training us with the tools so that we can increase our representation in the media. So hopefully you'll be hearing more and more about our research, and hopefully soon we'll be in a position where for every man that you see talking about science or technology in the media, you'll also see a woman. So that sort of brings me full circle back to this question of what will environmental engineering look like in the 21st century? Well, it just so happens that many of the major challenges that we face as a nation and as a world fall right into the remit of environmental engineers. I don't think there's ever been a better or more empowering time to be an environmental engineer, or to really have the chance to make an important difference in the future of our country. And what I'm hoping that difference looks like is a little bit like our kind of detailed approach. I would love to see the people who have the knowledge in those detailed areas. So we have engineers, scientists, researchers, policymakers, the general public as well, bringing together our understanding of that detail so that we can collaborate and make a big picture that is really going to be meaningful and useful for everybody. I'd like to see advanced technologies informing this detailed understanding of our natural systems, so that we've got evidence-based, we've got accurate predictions from which the policymakers can move forward. And I'd like to see engineers developing innovative and resilient solutions, drawing on the diversity of their teams to do this. And finally, my hope is that engineering by the end of the 21st century is seen as an accessible and desirable career for everybody, whatever sector of society they come from, because engineering is all about ideas generation, and we need everybody's ideas if we're going to tackle the challenges of the future. So that's it from me. I'm very happy to take questions if anybody has any. I'll pass back over to Sam now.
That's great. Thank you so much, Ellen, for such an insightful and inspirational presentation. We actually have had one question just come through, but the more the merrier. So please take the opportunity now to write any questions into the question box, hit submit, and we'll get to as many as we can. The first one's come through from Mojo, who asks, how do you integrate between large-scale aspects of enviroengineering, such as catchment management, save for river health, I believe, with minute aspects of your research?
Oh, Mojo, that's an excellent question. I think what it really takes to integrate those kind of two scales is a team of people with expertise across those different scales. So I think it is really important to be able to understand how the water and the soil interact in that kind of chemical space. But equally, there are other factors that are really important in that, in the bigger scale catchment management that you raise there. So understanding water flows, the hydrology, the water sources that are coming together, because that will influence the water chemistry itself. So I do think it's really important as we move forwards as environmental engineers to take this kind of collaborative approach. Everybody has their individual areas of expertise, and in isolation they're perhaps not that useful, but I think if we can bring them all together and work in teams, then that's the best way for us to really bring sort of constructive management to systems, big systems like catchments.
Great. So yes, please do send those questions through. We've got some time now, so it'd be great to hear from anyone who had some burning questions. I had one while I was listening, just interested to know what first interested you in studying in this discipline or getting involved.
I don't know. See, I'd always loved science at school. It was always my favourite subject, and I didn't really know what I wanted to study at university, and my careers advisors at school just said, well, stick with what you know, stick with what you enjoy. And so that's what I did. That's what led me to chemical physics. And then, as you saw from my career pathway, it's taken a few turns and a few sort of sideways movements, but that's the great thing about a STEM training, is that I do think it's very transferable. There are a lot of skills that you learn that are very applicable. You know, how to research is a very important one, but similarly, a good grounding in chemistry, physics, maths will really enable you to kind of move in any direction in engineering that I think that people would want to go.
Great. And it sounds like from that example that you had support from your science teachers and from people at school. I mean, what kind of role do you feel that teachers have in encouraging these kind of career paths, and do you see it changing?
Yeah, that's a really good question. I think teachers play an incredibly important role, as do parents, in guiding young people in their choices. And I know that in the past, it's some science teachers or some careers teachers and parents have been hesitant about pushing their children towards, or encouraging their children into STEM careers, because they worry that it can be a little bit of a hostile environment perhaps. But I would say that that's definitely not the case. And if you have a child, or you know a child who has that inquisitiveness and really loves science, then definitely encourage them to pursue it. You certainly don't have to be the best at science in your class. You certainly don't have to be the best at maths in your class to be able to make a successful career out of it if you have that curiosity. So I would very much encourage people to stick with STEM if they are enjoying it.
Excellent. There's a question come through from Brendan, who asks, have you used your research outcomes to provide guidance and advice to prevent environmental issues such as need for remediation?
Yeah, that's a great question, Brendan. The ultimate aim of everybody's research is to be able to have that kind of real life impact. And some of the work that I did during my PhD has, it's a slightly sort of convoluted way to explain it, but the work that I did during my PhD generated some numbers that are pretty important for environmental models, and by being able to constrain those numbers and refine those numbers that are then inputted into the models that often people use for environmental management and those types of things. I guess my work has sort of indirectly contributed to that aspect of remediation. But in terms of some of the work that we were doing in North Queensland, that was a lot more hands-on and a lot more sort of direct in terms of the impacts of remediation, and also the effects on policy around the management of acid sulfate soils. So there we were very lucky that we were working directly with a landowner who was the Queensland government, and also the traditional landowners as well. to sort of on-site remediate and monitor, and through those processes that was a kind of much more direct application of my work and the work of others to sort of real-time remediation.
Great. Well, unfortunately, we're probably out of time for more questions now, and it sounds like people have asked the ones they've thought of, but if anything else comes to mind and you're in the audience, please feel free to send them through to our alumni office. We can pass them on to Dr. Moon. And we'll just run through a couple of quick slides regarding our alumni relations program. So we've got a presence on social media, on Facebook and LinkedIn, and we'd love to hear from you, and you can hear about lots of great things that are on offer for our alumni community, so please do follow us. Also, just a reminder that alumni are eligible for a 15% bursary in postgraduate education, which is a really great resource. So you can find more information on the Deakin website, or you can email deakinalumni@deakin.edu.au. We also run a number of competitions throughout the year. Generally, the information about that is shared on social media and also through our e-newsletter, Deakin Times, which goes out once a month as long as we have a valid email address for you. So please do get in touch with our office if you don't receive that and would like to. You can also share your postal address if you'd like to. Then we'll invite you to events that are near where you live. We have interstate and international events throughout the year, so please do get in touch with our office. Thank you once again for joining us. Thank you, Dr. Ellen Moon, for your insights and time.
It's okay.
And if you want to provide any feedback for us, the email address is deakinalumni@deakin.edu.au. Thank you and have a great day.